All right. So we've been through the derivative rules. We did some extremely good review of all those setups. And so what comes next, calculus wise, is if we've learned a good thing, we've kind of been through different examples of how to find a lot of derivatives. We've done some different applications. We've found maximums. We found minimums. We found increasing. We found decreasing. We did related rates. We did it all. So what comes next is let's see if we can reverse this process, right? So, uh, what good is it to sort of do something going one direction? Let's see if we can't flip it around and sort of run it the other way. So, doing integration and finding antiderivatives. These sort of things are all kind of different ways of sort of describing the same process. So an integral, right, is the notation that we use to sort of find an antiderivative. An antiderivative is essentially exactly what it sounds like. It's sort of doing the derivative process in reverse. So we have sort of an antiderivative power rule where rather than sort of subtract the power and sort of multiply, you end up adding to the power and then you divide, right? So some of the rules have a very natural kind of way to sort of reverse them and flip them around. Some of them maybe not so much. We're going to look at all of it. So what I want to do, I had sort of just as practice started to write out a list of the different sort of basic integration rules, the sort of basic integrals. And honestly, it looks semi-decent. So I'm just going to keep it and we'll just sort of talk through it. And then, of course, we'll do a separate video where we do some integral examples to kind of get ourselves situated, make sure we know what we're talking about. So integration rules, excuse me. The notation here, right, is the integral, is this sort of stretched out s kind of thing. And then there's a dx. So, right, you remember from our derivative notation, d over dx, the x in dx tells us what the variable is, what the variable is we're doing everything with respect to, right? What's a sort of, what's moving around, and that has a lot of implications about, if you have different variables involved, obviously, x's go with the x's and so on and so forth. So if I'm trying to do an integral and I don't have any x's in my situation, all I have is constants, just a constant value, pi or 3 or 5 or whatever. If I want to do an antiderivative, if I want to integrate that, what I'm going to get is just the constant times x. And then every integral, this is what we call the indefinite integral, because it's just purely finding an antiderivative, has plus big C on the end. Big C is, of course, our sort of generic constant. The idea here is if you find an antiderivative, right, if you do this integration process, find an antiderivative, in theory, it could have had some constant tacked onto the end of it that when you took the derivative, that constant went to 0. There's not really any way of knowing. It's a little bit different. When you take a derivative, you get sort of one definitive derivative out of it. If you do an antiderivative, you lose a little bit of precision because you could always have sort of plus minus some value in your original, your sort of original starting function, right? If you're thinking of the original function that you're getting to is this sort of antiderivative. So a constant would sort of backtrack to the constant times x, right? Because if you did the derivative of something times x, the x would go to 1, and you'd just be left with the constant, the little c. So then the x comes back, and you have plus big C, right? This generic constant on the end that sort of is just always there. So that would be the sort of most basic possible version, right? If we just start with some sort of number, some sort of value, that's what we would get. If we want to reverse engineer the power rule, right? So one of our just like most foundational go-to derivative rules. If I want to do an integral, right? Find the antiderivative of x to a power. This is going to work for any power that's not minus 1. There is a little bit of a restriction there. We can't do minus 1 as our power. Any other power is good to go. So x to the power, the antiderivative, right, the integral, what's going to happen is you're going to add 1 to the exponent, and you're going to divide by that new power. So it's x to the n plus 1, divide by n plus 1, as always, plus our generic constant, big C. Anytime we're doing what we call an indefinite integral, which is there's no values here, this is just a generic antiderivative, a generic version of it, you have to have plus big C. Don't forget, this is the most frustrating thing in the world. If you're on a quiz or in your homework or something, you do all this work and you forget the C, they're going to tell you it's wrong, right? So always make sure you have your plus C's on there, and all that hard work isn't for no reason. So this is very much, it looks almost like what an inverse function would be, right? Because we're just very directly reversing all of the different steps that we would normally take, right? A derivative is your multiplying in front and you're subtracting from the power. This is adding to the power and dividing, right? So it's very obviously sort of the reverse of what we had done. A couple generic rules. Oh, this is plus or minus, actually. If I have a constant times a function, or if I'm trying to add or subtract two functions together, right, plus minus, or some sort of constant times a function, if I do an antiderivative, none of those things really have a big effect. If I have a constant in front, in theory, I can just pull the constant in front of the whole thing and just do the antiderivative of whatever the function is. The constant doesn't make a difference. It doesn't have an impact in as much as it just stays there, and then you're going to multiply it by the final version. Similarly, sort of addition subtraction, you can break up this antiderivative process, finding an integral. You can just break it up over addition subtraction. So if you have 2, 3, 4, 5, however many things all sort of added, subtracted together, just break them up and just do them one at a time. Sometimes that's very, very helpful, and you really get very different answers sort of from one piece to the other. If it's just a polynomial or something, then you're kind of doing this without even really thinking about it, and you can kind of take it for granted. So obviously, as we get to more advanced techniques, we'll sort of talk about when these things come into play and when they're very important. Couple standards, right? So some extremely good ones. We know the derivative of e to the x is e to the x. That must also mean that e to the x is its own antiderivative, right? So if I reverse that process, the integral of e to the x dx would equal e to the x, of course, plus big C. So there is a limit there, right? We can't necessarily just keep going back and back and back forever, because in theory there could be constants that are here, and if we tried to go again, whatever this constant is, that's going to start to have an x attached to it, and then another constant comes up, and these things sort of build on themselves. We said before, for the power rule, we can't do the exponent -1. I think I said that. Maybe I didn't say that, but it's written here. If I try to do a power rule with that, you can see part of this is obviously if my original power is -1 and I add to that, then I get 0. We're dividing by that power. We can't divide by 0, right? It gets us an undefined value, yada, 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 some stuff with limits. But in general, right, we can't really do that. So what the heck is going to happen? Well, what was the function that gave us 1 over x, right, x to the -1, as a derivative? And the answer was natural log of x, right? The derivative of natural log gave us 1 over x. Natural log of x gave us 1 over x. And so that means if I'm doing an antiderivative of 1 over x with respect to x, I'm going to get natural log of x. Natural log as a function is not allowed to sort of take any negative values or 0. So we're going to do natural log of absolute value of x. We need the absolute value sort of tacked on there. Just as sort of a fail-safe, right? Our natural log only really deals with positive values. And that's the idea. A couple quickies just to sort of run this through. Just our trig integrals, right? So this is essentially just all of our trig derivatives run in reverse. So the derivative, how would we do this? So the derivative of cosine is negative sine. So then if I want to do an integral of sine, I would get negative cosine as the antiderivative, right? The derivative of sine is cosine. So then if I want to do the integral, the antiderivative of cosine, I would get positive sine. The plus minuses here, obviously they go back and forth between each other. The plus minuses, you just have to slow down and sort of think about which direction you're going and sort of when and where the positives and negatives show up. It can be annoying, nevertheless, it is what it is. All their trig functions, right, things tangent, cotangent, secant, cosecant, had more unusual, still trig-based derivatives. So then the antiderivatives we're looking for or rather the integrals and the antiderivatives that we're going to get are based off of those trig derivatives, right? So I don't really have just a basic integral of secant, but I know secant squared is the derivative of tangent. So if I could do an integral of secant squared, right, of x dx, it'll go backwards to tangent. Cosecant squared would go backwards to sort of a negative cotangent. Again, we're sort of dealing with the positives and negatives there, right? As they come, a positive or a negative is pretty easy to deal with. Secant, right, has secant times tangent as its derivative, so then that means I can integrate secant x times tangent x dx. I can send it backwards to secant, or cosecant times cotangent of x, right? Go backwards to negative cosecant of x. All of these, of course, plus big C. You know, these are not the kind of things you would just say like, oh yeah, I'm just walking in the woods and I stumble on secant of x times tangent of x. So that's a little bit more contrived in some sense, right? It's not the same thing as just saying what is the antiderivative of tangent of x. You know, those antiderivatives exist, but we're going to need some more advanced stuff before we can actually kind of deal with them. What else? Oh yeah, we'll do 3 of the inverse trigs. Whoops, let me try to get this back into frame. 3 of the inverse trigs to sort of wrap up this list for now. Gosh darn it. Gosh darn it. Right, so arcsine, arctangent, arcsecant, right, the inverse for sine, tangent, and secant. Those are our positive versions. We said previously, right, the derivatives of arc cosine, arc cotangent, and arc cosecant, right? The other 3 are just negative versions of the same thing, so it's kind of redundant to have all 6 of them listed. You could always do a negative to a negative and vice versa. So these are very particular forms, right? So these arc, these inverse trig derivatives had very particular forms. So as far as doing an integral, we would need a very particular version of something to start out with. So if I have an integral 1 over, right, the root of 1 minus x squared, that would go backwards to the arcsine of x, right? That very particular setup. 1 over 1 plus x squared, right, will go backwards to arctangent of x. Again, it's this very, very particular setup. You know, this is not the thing that really works, you know, as a great general rule, but that's kind of what we have to deal with right now, right? We have some of these very specific derivatives, so we want to have a list of all of the things that those would sort of reverse back to, so we can catch them. In theory, that's the easiest integration we have. It's just if it's on our list, we can sort of just run it. Right, 1 over x times the root of x squared minus 1 is going to go backwards to the arcsecant of x, right? All these again plus big C. So this master list, these are the kind of integrals, right? This is the kind of stuff we're going to be sort of on the lookout for. These are the kind of things we can integrate in theory in one step, right? If I see one of these as a part of a problem, I can just do the antiderivative, right? Kind of, you know, referencing this, referencing our notes if we've got them. You know, we want to probably make a table of integrals, right? Standard integrals. We want to have all of these on there so that we can, right, just sort of solve some of these in one if we see them. We're going to be doing lots more advanced stuff, but we kind of need these like foundational things first. We'll do one more video with some examples, some integration examples, so we can kind of see this working. That'll be that for our review.